everyone. In today's video, I'll be telling you about Kirchhoff's current law, which is one of the essential concepts in electrical circuit analysis. So let's begin by stating the Kirchhoff's law, Kirchhoff's current law, or Kirchhoff's first law, which states that the algebraic sum of currents at a node is zero. In order to understand this better, we should first know what the term node here really means. So, a node could actually be of two types. The first type is a simple node, and the second one is called a principal node. So, a simple node is one where you have just two components connected. So, for example, if I have a voltage source connected to a resistor, so here, this particular point or this particular point would be a node. Both of these points are one and the same node. So I can name it as N. But here, there won't be any division of current because the current that comes will not get divided anywhere over here because there's just one node. Now, what is a principal node? If there are more than three elements connected to a particular node, then that becomes a principal node. For example, if I have a voltage source with a resistor and another resistor over here, and maybe another one, and so on, then this particular node is called a principal node. Why? Because to this node, there are three components connected: this voltage source, this resistor R1, and this resistor R2, which is connected to node N. So that is the difference between a simple node and a principal node. So here when we look at a principal node, there is a possibility of division of current. What does that mean? So if there is a current which is entering this node, when it leaves the node, it might so happen that the current will get split up because a part of the current would have to enter one of these branches and the remaining will enter the other branch. So that amount of current which is going to enter a particular branch will depend upon the resistance of that branch. In this circuit which is shown over here, let us try to identify the nodes. So over here, this is one node. Why? Because there are two components connected to it, this voltage source and this resistor. So I'll call this as N1. Then this is another node, N2, where you can say that this resistor and this resistor are connected. We could think that this is another node, but this point and N2 are one and the same because there are no other components connected in between. So we are not going to consider that as a node. Now, let's come to this side of the circuit. Here, all the three components are connected to a node, which would probably be grounded or connected to the negative terminal. So that would be called as N3. So there are essentially three nodes in this circuit. Now, having understood the concept of node, let us go back to KCL. So here we see that the law states that the sum of currents at a node is zero. What does that mean? So let's analyze node N1. At N1, there are three currents that are actually operating. What are they? So there is one current over here, one over here, and one over here. So basically, there is a current I which is entering the node N1. It splits up. A part of it goes out and a part of it goes down into this resistor. I'll call it, say, R1. So when you look at this node N1, the total current I is entering and it splits up into two. One part is I1. The other part is again going to split up into two because this particular current, let me call it as I dash. So I dash, what happens to I dash is a part of it goes into, say, R2 as I2 and the rest of it goes into, say, R3 as I3. So I dash again splits up as I2 and I3. So this is what is happening at all of these nodes, right? So see, this part is happening at node N2 and this split is happening at node N1. At node N3, all of these currents are combining together. So from here, I'm going to get I1, from here, I'm going to get I2, and from here, I'm going to get I3, which will combine at node 3 and come back as I. Let us now try to write the KCL equations for these two nodes. So we are going to get two KCL equations. So one will be for node 1. So for node 1, let's look at the currents that are associated with node 1. The first current is I, which is entering N1. Then we have I1, which is leaving N1, and I dash, which is again leaving N1. So these are the three currents associated. Now let's consider this node to look like a basket. So if I'm going to put a fruit into this basket, I'm adding a fruit. But if I remove a fruit from this basket, I am subtracting a fruit from this basket. Same way, if you look at a node, a current which enters the node, I'm going to put a positive sign for it. But the currents which leave a node, I'm going to put a negative sign for it. So now I'm framing the KCL. At N1, I is entering, so I'll put a plus sign. I1 is leaving, so I've put a minus sign for it. And I dash is also leaving N1, so I'll put a minus sign for it. The law states that the sum of all these currents is going to be 0. So basically, it boils down to the equation that I is equal to I1 plus I dash, which is pretty intuitive. Now let's look at node N2. At N2, right? So here again we have I dash, which is entering, so it will have a positive sign, but I2 and I3 are leaving, so we'll have a negative sign for it. So writing the KCL equation for node N2, what are we going to do? We are going to have I dash with a positive sign, I2 and I3 with negative signs, and all of this put together sums up to 0. So this basically turns out to be I dash is nothing but I2 plus I3. It's that simple. So this is how we write a KCL equation for a particular node. Now let's try writing the KCL equation for this particular node over here. So there's just one node, I'll call it N1. Assume that there are some resistors connected to these random branches which are shown. So here I1 is entering N1. So I'll say plus I1. I2 is leaving N1. So it'll be minus I2. I3 is entering N1. So plus I3. I4 and I5 are leaving N1. So minus I4 minus I5. All this put together is 0. So we can say I1 plus I3 is nothing but I2 plus I4 plus I5. So this is the KCL equation for this particular node. So that's all about KCL. I hope this video was useful to you all. Both KVL and KCL form very important tools in solving complex circuits and simplifying them. Thanks for watching. Please do subscribe to my channel.